Okay, looking at question 4 from the 2021 summer paper. Now this is about this plots of, we've got years, carbon dioxide, and we've got some measurements that are made, and then there's a straight line that's fitted through that. And I tell you that the equation of that straight line is y equals 1.704x minus 3056.6. So y is the concentration of CO2, which is in parts per million, and then years, which is x, which is in years. And then the first part of the question I ask you is what are the units of each part, each of the terms which are in here. So y is in parts per million, because that's the that is what CO2 is measured in. Now this 1.704 is the gradient of the plot, and gradient is y divided by x, so that's parts per million per year, and then x is in years, and then this last bit is the intercept, which is where the line would cross the y-axis for x equals 0. So that's also going to be in parts per million. We can see here that years and years cancel out. And this isn't really part of the question, but just to show you that if we've got parts per million and then we've got a sum, we can't have parts per million subtract away years, or years take away parts per million. So each of these terms has got to be parts per million. Okay, so the answer to that question is the units of y are that, the units of x are that, sorry, the units of the gradient are that, the units of x are that, and the units of the intercept are that. Okay, part B asks you to imagine that there's a policy of reducing CO2 concentrations to their 1990 levels by 2050. What's the difference between the target concentration and the one that would be estimated from this business as usual linear model? Okay, so we need to work out, well, what would the concentration of CO2 be in 1990 and 2050. So to do that, we just enter in x equals 1990 into our equation here, and if we do that, we get y, which is the concentration of CO2, so square brackets this time, meaning the concentration of in parts per million is going to be 335.4, so it's 335.4 parts per million. And then for x equals 2050, the concentration of CO2 is going to be 457.6 parts per million. So it's literally all I've done for this here. I'm not going through the calculation because I put that in a calculator previously, but you just put in the value of x, so for 1990 and then x for 2050. Then the question then it asks you what's the difference between these two? So how far, if we were to follow CO2, if it was going to grow according to this model, by 2050 it would be this concentration, but actually what they want is the concentration to be this. So what's the difference between these two? So big one minus little one. The difference is 102.2 parts per million. Okay, so that's the answer. That's the answer to that question. Okay, part C. So this question it's maybe deceptively simple actually. So what it says is what would the mass of carbon need to be removed by 2050 in order to get it back down to 1990 levels? So we told you there's an extra 202 parts per million. That was the answer to the previous question of CO2 in 2050 compared to 1990, i.e. this is the amount that's too much in the atmosphere. This is the bit that we'd need to remove. Okay, so the other thing they tell you is that 1 part per million of CO2 is equivalent to 2 petagrams of carbon emissions, where 1 petagram equals 1 times 10 to the 15 grams, i.e. it's a very big number. So for this, all we then need to do to convert this into a mass of carbon, we just multiply 102.2 times 2, because that's what 1 part per million is. We want to know what 102.2 are, and so hopefully you don't need a calculator for that. So that's 204.4 petagrams. Okay, and then it asks what petagrams of carbon, if we're going to be absolutely correct. And then the other thing, I asked you to write that in scientific notation, and also to report the answer in grams. So that would then be 2.044 times 10 to the 17 grams of carbon. Okay, so what I did there is, because 1 petagram is 10 to the 15 grams, we multiply that first by 10 to the 15, and then to write it in scientific notation, where this number here has to be less than 10. So therefore I had to sort of shift the decimal point. Okay, don't want to spend too long going through things like that, because I think that you would be able to do that yourself. Okay, question D. Okay, so each question sort of builds on here. So this question D asks you, a large-scale carbon sequestration project gets underway by 2025. What would the rate of carbon uptake need to be in order to remove enough carbon to get CO2 to the 1990 target concentration by 2050? So here, this is the amount of carbon that we need to remove. So 2025 to 2050 is 25 years. So it's 204.4 divided by 25 gives you 8.18 petagrams carbon per year. Okay, so if that's the amount of carbon that we would need to remove, assuming that the CO2 concentrations are going up, as they are according to that linear model, we need to remove this much carbon in order for the CO2 concentrations in the atmosphere to be down at the 1990 level. And if we're starting to remove that in 2025, we've got 25 years to do so, this is the amount of carbon that would need to be removed per year. Okay, so a lot of this isn't very difficult sums, by the way, but it's more difficult in translating some of these numbers into what sums that you would need to do. All right, so we're moving 204.4 petagrams over 25 years, so that translates to this 8.18 petagrams of carbon per year. Okay, last question. So assuming that tropical forests absorb carbon at the rate of 5 tons per hectare per year, what do we, how much land area of the Earth, I'll read the question exactly. Expressed as a fraction of the Earth's land area, what is the equivalent area of tropical forest needed in order to remove the amount of carbon identified in part C? Okay, so we've got, we need to remove 8.18 petagrams of carbon per year. So, and then we need to know how many hectares would we need, and we're told that. So this is the amount the removal per year, and we know that a tropical forest removes 5 tons of carbon per hectare per year. Okay, so the easiest thing probably just to convert these straight into grams, so we're not having to think too much about working with all these different prefixes here. So let's think about how many hectares do we need. So it's going to be this divided by this. This is going to then get us the answer, an answer in hectares. So if we do 8.18 times 10 to the 15. So that's gone from petagrams, we're now in grams. So that's how much we need to remove in a year. And because we're talking per year here for removal as well, so we don't need to worry about this aspect of it. So we're just going to think about like how many hectares would we need in a year, basically. So it's going to be the same answer in 2025 as it is going to be in 2050. Okay, so this is the amount of carbon we need to remove, and tropical forests can remove 5 times 10 to the 6, that's what a ton is, grams per hectare. So if we just look at this, now the grams will cancel out and we'll be left with 1 over hectare. So if we just think about our units just as an aside, 1 over HA to the minus 1 is the same as a hectare, okay, which is what our units are. So hectares equals this. So if we stick that in our calculator, then we get 1.62 times 10 to the 9, roughly 1.6 billion hectares is what we'd need in order to remove 8.18 petagrams of carbon every year, assuming that each of these hectares takes up 5 tons. 5 tons. Okay, so that's that one bit of the question. Let me just quickly move to another sheet. So the question is now to express that as a fraction of the Earth's area. So I'll tell you in the question we can think about the surface area of a sphere is 4 pi r cubed. So area equals 4 pi r squared. And then I tell you that roughly 70% of the Earth's surface is ocean, therefore 30% is land. So we say the area, which is land, is 4 pi r squared times 0.3. Write that like that. Okay, so that will give us the area of the whole sphere, but we just want 30% of that sphere. Okay, so again, if you stick that in your calculator, you'll get 1.54 times 10 to the 14 meters squared, because I give you the radius in meters. Okay, and then one hectare is the same as 10 to the 5 meters squared. So we then just divide this number by 10 to the 5. Okay, so this is our side here. So this then becomes 1.54 times 10 to the 9 hectares. Okay, so all I've done there is we've divided by 10 to the 5. Okay, again, if you want to, not going to go through all the unit conversions here and how to do that, but you can go back and look at the questions about how to do it. Okay, so from our previous answer, we know that we need 1.62 times 10 to the 9 hectares. The total land area that is available on Earth, let alone available to make into tropical forests, is 1.54 times 10 to the 9 hectares. So let's express this as a fraction or even as a percentage. So there'd be 1.62 divided by 1.54 times 10 to the 9. If we multiply that by 100, express it as a percentage, we get 105%. So essentially it's impossible. If we wanted to remove that carbon starting in 2025 using tropical forests, it is impossible for us to get back to 1990 levels of CO2. Now, you know, this is a very simple calculation, back of the envelope, lots to pick holes in it, and obviously we're really dwelling on the maths here. But hopefully you can see how those equations bring together, and hopefully you can see how there's maybe a kind of an interesting answer too.